7 asteroids that had been cataloged as Mars Trojans, objects in stable orbits sharing Mars' path around the Sun, were no longer where they were supposed to be. Not just slightly off, the kind of deviation you might see from perturbations or measurement errors. They were gone. Departed from the Lagrange points that had held them, moving on new trajectories that would take them away from Mars entirely, and all 7 had left within the same 2-week window in mid-January, right after 3I Atlas passed through the Mars Trojan region on its way out of the inner solar system. Let me back up and explain what Mars Trojans are because they're not as well known as Jupiter's Trojans or Earth's few Trojan companions. Lagrange points are positions in space where the gravitational forces of two large bodies, say the Sun and Mars, balance with the centrifugal force felt by a smaller object, creating zones of orbital stability. There are 5 such points for any two-body system. 3 of them are unstable. Objects placed there will eventually drift away, but 2 of them, called L4 and L5, are stable. Objects that end up there can stay for a very long time, wobbling around the equilibrium point but never straying too far. For Mars, the L4 and L5 points are located 60 degrees ahead and behind the planet in its orbit. Picture Mars moving around the Sun and imagine points at the leading and trailing vertices of an equilateral triangle with Mars and the Sun at the other 2 vertices. Those are the Lagrange points. Asteroids can get captured into those regions through various dynamical processes, and once there, they're stuck in a relatively stable configuration. They orbit the Sun with the same period as Mars, maintaining roughly the same position relative to the planet. Mars doesn't have a large Trojan population compared to Jupiter, which has thousands of known Trojans, or even Earth, which has a handful. As of early 2026, there were only about 30 confirmed Mars Trojans, most of them discovered in the last 2 decades as survey telescopes got better at finding small, faint objects. They're small asteroids, typically a few hundred meters to a few kilometers across, dark and rocky, probably captured from the main asteroid belt at some point in the past few billion years. Not particularly interesting individually, but collectively they provide information about the dynamical history of the inner solar system and how objects migrate between different orbital zones. Dr. Apostolos Christou from the Armagh Observatory in Northern Ireland has been studying Mars Trojans for over a decade, tracking their orbits, measuring their properties, using them as test cases for understanding orbital stability in the inner solar system. His team maintains a database of all known Mars Trojans, updating their orbital parameters as new observations come in. In early February, while processing data from various observatories that had been tracking these objects over the past few months, he noticed that several of them were missing. Not missing in the sense of lost to observational uncertainties. Missing in the sense that when you calculated where they should be, based on their known orbits, and looked at that position with a telescope, they weren't there. The first one he noticed was 5261 Eureka, the largest known Mars Trojan at about 3 kilometers in diameter, a well-studied object that had been in the Mars L5 point since its discovery in 1990. Observations from January showed it right where expected. Observations from late February showed it gone from L5, now on a trajectory that would take it out of the Mars resonance entirely within a few years. That was surprising enough to trigger a deeper investigation. Dr. Christou and his team went through the observational data for all known Mars Trojans, pulling records from the Minor Planet Center, checking amateur astronomer databases, reaching out to colleagues who'd been observing Mars-crossing objects. They found 6 more. 1999 UJ7 2001 FR 127 2007 NS2 2011 S C191 2011 SL25 and 2011 UN63. All of them had been stable Mars Trojans, 3 at L4, 4 at L5, and all of them had departed their Lagrange point positions sometime in mid to late January 2026. 7 objects out of 30 known Mars Trojans, nearly a quarter of the entire population, simultaneously leaving stable orbits. That's not normal. Orbital resonances can be disrupted by planetary perturbations, by close approaches to other bodies, by non-gravitational forces like the Yarkovsky effect, where absorbed sunlight creates tiny thrust. But those processes work slowly, gradually shifting orbits over thousands of years. They don't cause multiple objects to leave simultaneously, and they certainly don't affect objects separated by hundreds of millions of kilometers all at once. Dr. Christou started looking for what else happened in mid-January that might be relevant. Planetary positions, close approaches, anything unusual in the inner solar system, and he found it. 3I/Atlas, the interstellar comet that had passed through the inner solar system in late 2025, had crossed Mars's orbital plane on January 14, 2026, and its trajectory had taken it directly through the Mars L4 region. Not a close approach to Mars itself, the comet passed about 0.6 astronomical units from the planet, but it went right through the volume of space where 3 of the departed Trojans had been orbiting. That was a potential explanation. A gravitational encounter with the comet could have perturbed the Trojans, given them velocity kicks that destabilized their orbits. Except when Christo ran the numbers, when he calculated the gravitational influence that 3I Atlas would have had on objects at the distances involved, the effect was far too small. A comet nucleus a few kilometers in diameter has mass of maybe 10 to the power of 14 to 10 to the power of 15 kilograms. The gravitational pull from such an object at distances of millions of kilometers is negligible. You could pass a comet through the Lagrange points and the Trojans wouldn't even notice. To actually kick a Trojan asteroid out of its stable orbit, you need a significant velocity change, something on the order of tens to hundreds of meters per second, depending on the specific orbital geometry. Getting that kind of delta V from a gravitational encounter requires either a very massive object or a very close approach. 3I Atlas was neither massive enough nor close enough to any of the 7 asteroids to provide the necessary kick, not individually and certainly not to all 7 simultaneously. But the timing was undeniable. Before January 14th, all 7 Trojans were in stable orbits. After January 21st, all 7 were departing. The week-long window corresponded almost exactly to the period when 3I Atlas was transiting through the Mars-Lagrange regions. If it wasn't gravitational influence from the comet, what was it? Dr. Christo reached out to colleagues at NASA's Jet Propulsion Laboratory, specifically the team that tracks near-Earth objects and calculates close approach probabilities. He wanted independent verification of the orbital changes and help understanding what could cause such synchronized departures. Dr. Davide Farnocchia, who specializes in orbit determination for small bodies, took the data and ran it through JPL's high-precision orbital simulation software, using the most accurate planetary ephemerides and accounting for all known gravitational and non-gravitational forces. The results confirmed what Christo had found. The 7 Trojans had all undergone significant orbital changes in mid-January. The magnitude of the changes varied. Some objects got larger velocity kicks than others, but all of them were now on trajectories that would remove them from Mars resonance. And when Farnocchia calculated backward, when he tried to figure out what force or encounter could have produced those orbital changes, he came up empty. No planetary close approaches, no asteroid-asteroid encounters that anyone knew about, no plausible non-gravitational mechanisms operating on the right timescale, except 3I Atlas passing through the region. But again, the mass was wrong. Way wrong. To produce the observed orbital changes through gravitational interaction, 3I Atlas would need to be roughly 100 times more massive than observations suggested. That would make it not a comet, but a small moon. Something with a mass comparable to Phobos or Deimos, the tiny moons of Mars. But everything about 3I/Atlas, its brightness, its outgassing behavior, its spectroscopic signature indicated a cometary body just a few kilometers across, not a massive object. Unless the observations were wrong, unless there was mass there that wasn't visible, that wasn't emitting light or producing the signature you'd normally see from a rocky or icy body. Dark matter is one possibility, though concentrating that much dark matter in a comet-sized volume violates everything we know about how dark matter behaves. A collapsed core, maybe? Some kind of ultra-dense material at the center of the nucleus. But that would show up in other ways, in the object's response to tidal forces, in the distribution of mass inferred from rotation dynamics. Dr. Farnocchia ran a statistical analysis to quantify just how improbable the synchronized departures were. He calculated the baseline rate at which Mars Trojans naturally leave their resonance due to planetary perturbations and other known mechanisms. It's a slow process. Based on dynamical models, you'd expect maybe 1 Trojan to depart every few 100,000 years. The probability of 7 departures happening within the same 2-week window by pure chance, without any external trigger, came out to approximately 1 in 1.2 billion. Not impossible, but so unlikely that you'd be justified in looking for a causal explanation, rather than attributing it to coincidence. And the correlation with 3I/Atlas's passage was strong. Too strong to ignore. The timing was too precise, the spatial overlap too exact. 3 of the departed Trojans had been directly in the path of the comet's trajectory through L4. The other 4, while not in the direct path, were within the general region that the comet transited. If you plotted the comet's path through the Mars orbital plane and overlaid the positions of the departed Trojans at the time of passage, they clustered around the trajectory line far more tightly than the Trojans that had remained stable. Dr. Christo prepared a preliminary report and circulated it to colleagues in the planetary dynamics community, asking for feedback and sanity checks. Had he made an error in the orbital calculations? Was there some mundane explanation he'd overlooked? The responses came back, generally confirming his findings but offering no obvious explanation. Several researchers pointed out that similar mass discrepancies had been noted in other contexts with 3I/Atlas. The object seemed to exert gravitational or dynamical influence beyond what its visible size and brightness suggested. That was troubling in its own right, but it at least meant the Mars Trojan observations weren't completely unprecedented. What made the situation even stranger was that the departures weren't random. When Farnokia analyzed the new trajectories of the 7 asteroids, he found they weren't scattering in all directions as you'd expect from chaotic gravitational interactions. 4 of them were now on trajectories that would take them toward the inner solar system, crossing Earth's orbital path within the next few years. 2 were heading outward, toward the asteroid belt. 1 was on a trajectory that would bring it dangerously close to Mars itself within 18 months, close enough for a possible atmospheric entry or surface impact. That directional bias, 4 out of 7 heading toward Earth-crossing orbits, was another statistical anomaly. Random gravitational kicks should produce random trajectory changes, with objects departing in all directions more or less equally. Instead, there was clear preference for inward trajectories. Dr. Farnokia calculated the probability of that happening by chance and came up with numbers even smaller than the probability of synchronized departure itself. If you combined all the improbabilities, the synchronized timing, the spatial clustering, the directional bias toward Earth-crossing orbits, you were looking at odds so long that invoking coincidence became absurd. Something had happened in mid-January when 3I Atlas passed through the Mars Trojan region. Something that affected 7 asteroids in coordinated ways, giving them velocity kicks that standard gravitational mechanics couldn't explain, sending a majority of them on paths toward the inner solar system, and whatever that something was, it was connected to the comet in ways that nobody understood yet. The Exodus, when asteroids leave home for no reason. Part 2 of 5. Let's look at the 7 asteroids individually, because the details of each departure tell part of the story. Dr. Christo and his team reconstructed the precise orbital evolution of each Trojan, using observations from multiple telescopes spanning from late 2025 through early February 2026. What they found was that while all 7 departures happened within the same time frame, the specifics varied in ways that were both informative and deeply puzzling. 5261 Eureka was the first one analyzed in detail, because it's the largest and best studied Mars Trojan. Before January, it had been comfortably settled in the Mars L5 point for as long as we'd been observing it, probably for millions of years based on dynamical models. Its orbit was textbook stable, librating around the Lagrange point with an amplitude of about 8 degrees, moving in a predictable pattern that repeated every few decades. Then, between January 14th and January 18th, its orbit changed. The libration amplitude increased dramatically, growing to over 40 degrees, which pushed it outside the stable resonance zone. By late February, Eureka was on a trajectory that would take it out of the L5 region entirely, heading toward a Mars-crossing orbit with a perihelion that would bring it closer to the Sun than Mars's orbit. The velocity change required to produce that orbital evolution was calculated at approximately 140 meters per second. That's substantial. To put it in perspective, that's about the same delta V that NASA's DART mission imparted to the asteroid Dimorphos when it deliberately crashed a spacecraft into it to change its orbit. Except nobody crashed a spacecraft into Eureka, and no known natural process imparts that kind of velocity change over a 4-day period to a 3-kilometer asteroid. 1999 UJ7, one of the L4 Trojans, showed a different pattern. It departed even more abruptly than Eureka, with the orbital change happening primarily on a single day, January 15th. Before that date, stable. After that date, on an escape trajectory from L4. The velocity change was smaller than Eureka's, about 85 meters per second, but it was applied almost instantaneously in astronomical terms. One day in resonance, the next day departing. Dr. Farnokia called it the cleanest impulsive maneuver he'd ever seen in natural orbital dynamics, then immediately caught himself because calling it a maneuver implied intention, implied control, neither of which you're supposed to attribute to asteroids. 2001 FR 127 and 2007 NS2, both from L5, departed together. Not just on the same day, but apparently at almost the same time, within hours of each other based on the trajectory reconstructions. They were separated by about 50 million kilometers in their positions around L5, nowhere near each other, no possibility of mutual gravitational interaction. Yet they both received velocity kicks around January 16th, both of similar magnitude, roughly 100 meters per second, both in directions that sent them on inward-heading trajectories. The synchronization was eerie, like watching 2 clocks in different rooms strike the hour at exactly the same moment when there's no connection between them. The three remaining asteroids, 2011 SC191, 2011 SL25, and 2011 UN63, all departed on January 17th, again within a narrow time window. Their velocity changes ranged from 75 to 110 meters per second. Two of them were sent inward toward Earth-crossing orbits. One was kicked outward, heading toward the main asteroid belt. All three had been at L4, and all three showed the same pattern of rapid, synchronized departure. When you map all 7 trajectories and trace them backward to their departure dates, you can see the sequence. January 14th, nothing. January 15th, 2 departures from L4. January 16th, 2 departures from L5. January 17th, 3 more departures from L4, all within a 72-hour window, and 3I/ Atlas, during those same 72 hours, was transiting through the Mars-Lagrange point region, moving from L4 toward L5 along a trajectory that took it through the volume of space where the Trojans orbited. Dr. Paul Wiegert from Western University in Canada, an expert on resonance dynamics and orbital stability, was brought in to review the analysis and provide an independent assessment. His first question was whether the departures could be explained by a resonance cascade, a situation where one perturbation triggers others through gravitational coupling between objects. It happens sometimes in dense asteroid populations. One object gets perturbed, its changed orbit affects its neighbors, they in turn affect others, and you get a domino effect. But the Mars Trojans aren't dense enough for that. They're spread across huge volumes of space, typically separated by tens of millions of kilometers. At those distances, the gravitational influence of one Trojan on another is essentially zero. You can't cascade a perturbation across that kind of separation. Each departure had to be independent, caused by an external force acting on each asteroid separately. Yet they were coordinated in time, happening in sequence as 3I Atlas passed through. Wiegert ran simulations trying to reproduce the departures using various assumed properties for 3I/Atlas. He gave the comet different masses, different density distributions, different shapes, trying to find any configuration that would produce the observed effects through normal gravitational interaction. Even pushing the parameters to unrealistic extremes, making the comet as massive as possible while still being consistent with its brightness and other observable properties, he couldn't get the math to work. The gravitational influence was always too small by at least a factor of 50. He tried non-gravitational mechanisms. Radiation pressure from the comet's outgassing, if it was massive enough, might exert force on nearby objects, but radiation pressure falls off with distance, and at the separations involved, multiple millions of kilometers, the force would be negligible. Plus, radiation pressure would push objects away from the source, not give them the specific velocity vectors needed to produce the observed orbital changes. Electromagnetic effects were another possibility. If 3I Atlas had a strong magnetic field, and if the asteroids had magnetic properties, there could be electromagnetic interactions. But comets don't have magnetic fields strong enough to matter at large distances, and even if they did, the asteroids would need to be highly magnetized themselves, which is unusual for the type of rocky bodies Mars Trojans are thought to be. Dr. Wiegert checked the literature on asteroid magnetic properties. There's limited data, but what exists suggests most asteroids have weak or no intrinsic magnetization, not enough to interact electromagnetically over millions of kilometers. That left increasingly exotic explanations. Maybe 3I Atlas had a massive but invisible companion, a dark object orbiting alongside the visible nucleus. That companion could provide the extra gravitational mass needed to perturb the Trojans. But if such a companion existed, why hadn't it shown up in any observations? You can sometimes detect companions through wobbles in the primary object's motion or through gravitational perturbations on other bodies during close approaches. None of that had been seen. Or maybe 3I Atlas wasn't a single object but a swarm. Dozens or hundreds of smaller bodies flying in close formation, collectively producing more gravitational influence than any individual piece. That's not unprecedented. Some comets have been observed to fragment into multiple pieces, but again, observations of 3I Atlas showed a single coherent nucleus, not a dispersed swarm, and a swarm loose enough to span the volume needed to affect all 7 Trojans would be spread over tens of millions of kilometers, at which point the individual pieces wouldn't be gravitationally bound to each other anymore. Dr. Christo compiled all the data, all the analyses, all the failed attempts to explain the departures through conventional mechanisms into a draft paper. He circulated it among co-authors in late February, and the discussion about how to frame the findings was contentious. Some researchers wanted to stick strictly to the observations and avoid speculating about causes. Just present the data. 7 Trojans departed. Here are their new orbits. Here's the timing correlation with 3I/Atlas. Make no claims about causation beyond noting the temporal and spatial coincidence. Others argued that you couldn't present such striking data without at least discussing possible mechanisms, even if those mechanisms were speculative or challenged existing understanding. The synchronized departures, the velocity changes, the directional bias toward Earth-crossing orbits, those weren't just interesting facts, they were phenomena that demanded explanation, and if conventional explanations didn't work, the paper should say so explicitly, opening the door for unconventional thinking. The compromised version, completed in early February, presented the observational data in detail, showed the statistical improbability of coincidence, and included a discussion section that systematically ruled out conventional gravitational and non-gravitational mechanisms. It concluded with careful language. The observed departures of 7 Mars Trojan asteroids coincident with the passage of interstellar Comet 3 EU Atlas through the Mars Lagrange point region represent a dynamical phenomenon not fully explained by current models. The velocity changes required exceed those that can be produced by gravitational interaction with a comet-sized body by approximately 2 orders of magnitude. Alternative mechanisms, including hidden mass, electromagnetic interactions, or undiscovered dynamical processes, warrant investigation. The paper was submitted to ICRIS, the International Journal of Solar System Studies, on February 8th. It was immediately flagged as high priority given the implications for near-Earth object tracking. If asteroids could be perturbed out of stable orbits by passing comets in ways we don't understand, that created uncertainties in long-term trajectory predictions. The 4 departed Trojans heading toward Earth-crossing orbits weren't immediate threats. Their closest approaches to Earth would be years in the future, and the trajectories didn't currently show high-impact probabilities. But if the mechanism that perturbed them wasn't understood, how could we be confident in those predictions? NASA's Planetary Defense Coordination Office requested a briefing on the findings before the paper went through full peer review. Dr. Farnakia presented the data to a group of NASA scientists, JPL engineers, and representatives from international space agencies via secure video conference in mid-February. The reaction was a mix of scientific curiosity and operational concern. The science side wanted more observations, more data, better characterization of what happened. The operational side wanted to know if this could happen again, if other asteroid populations might be vulnerable to similar perturbations, and what if anything could be done to predict or prevent it. The Exodus, when asteroids leave home for no reason. Part 3 of 5. The immediate question after the NASA briefing was how to find the missing mass. If 3I Atlas somehow had 100 times more gravitational influence than its visible size suggested, that mass had to be somewhere, either concentrated in the nucleus in ways that contradicted observations, or distributed in some configuration we hadn't detected yet. Finding it became a priority, not just for understanding the Trojan departures, but for assessing what other effects the comet might have had, or might still have, as it continued outbound from the solar system. Dr. Marina Brozovic at JPL, who specializes in radar observations of near-Earth objects and comets, proposed using the Goldstone Deep Space Network antenna to conduct radar ranging on 3I/Atlas. Radar can measure distance with extreme precision, and by tracking how that distance changes over time as both Earth and the comet move in their orbits, you can infer the comet's trajectory with much higher accuracy than optical observations alone. More importantly, any deviation from a purely gravitational trajectory, any acceleration that doesn't match what you'd expect from the sun's and planet's gravity, would show up in the radar data. The observations were conducted in late February, when 3I Atlas was about 2.4 astronomical units from Earth and still within range of Goldstone's powerful transmitter. The radar echo was weak, the comet was far away and not particularly reflective at radar wavelengths, but the signal was detectable. Dr. Brozovic's team collected ranging data over 5 nights, measuring the time delay between transmitted pulses and received echoes down to microsecond precision. When they analyzed the trajectory implied by the radar measurements and compared it to the trajectory predicted from optical observations and gravitational models, there was a mismatch. Not a huge one, but statistically significant. The comet was accelerating, moving faster than it should be, based solely on the sun's gravity and the initial velocity. The acceleration was small, about 0.002 millimeters per second squared, but it was persistent and directed generally away from the sun, consistent with what's called non-gravitational acceleration from outgassing. Except the magnitude was wrong. Comets do experience non-gravitational acceleration from asymmetric outgassing, where jets of gas and dust create small, rocket-like thrust, We see it all the time. It's a standard correction applied in comet orbit calculations, but the acceleration is usually proportional to the comet's activity level, how much gas it's producing. By late February, 3I Atlas was 2.1 astronomical units from the Sun, and its activity had decreased substantially from perihelion. The outgassing rate, measured spectroscopically, was down by a factor of 10 or more from peak levels. The non-gravitational acceleration should have decreased proportionally. Instead, it was roughly constant, as if something was providing steady thrust, regardless of how much the comet was actually outgassing. Dr. Brozovich calculated the thrust required to produce the observed acceleration. For an object the size of 3I Atlas based on optical observations, roughly 3 kilometers in diameter, the thrust came out to about 50,000 newtons. That's equivalent to a small spacecraft thruster, the kind of engine you'd use for orbital maneuvers on a satellite, but this was supposed to be a comet, a dead chunk of ice and rock with no engines. Where was the thrust coming from? You could argue that maybe the outgassing was more asymmetric than usual, concentrated in specific jets rather than distributed evenly across the surface. That could produce higher thrust per unit of gas released, but there's a limit to how efficient that can be. The gas molecules can only carry so much momentum, and you can only get so much thrust per kilogram of material ejected. Even under optimal conditions, the observed thrust would require ejecting about 2 kilograms of material per second. At that rate, over the months since perihelion, the comet would have lost thousands of tons of mass. That should show up as changes in brightness, changes in the coma density, changes in spectroscopic signatures, none of which had been observed at levels consistent with that much mass loss. It was the hidden mass problem in another form. Either the comet was more massive than observations suggested, which meant its density was impossibly high, or it was producing thrust through some mechanism other than normal outgassing. Neither option fit comfortably within standard cometary physics. Dr. Jean-Luc Margot from UCLA, an expert in asteroid radar observations and mass determination, suggested a different approach. Instead of trying to measure 3I/Atlas's mass directly, which was proving difficult, look at its effects on other objects. The departed Trojans provided data points. Each one had received a specific velocity change at a specific time when 3I Atlas was at a specific distance. If you could collect enough such data points, you might be able to constrain the mass distribution of the comet, figure out not just how much mass it had, but where that mass was located. The problem was, there were only 7 data points, the 7 departed Trojans. That's not enough to uniquely solve for a complex mass distribution. You need more encounters, more objects affected in measurable ways. Dr. Margot started looking through databases of small body observations, searching for any asteroid or comet that had passed near 3I Atlas during its transit through the solar system and might show orbital perturbations. He found 3 additional cases, not Mars Trojans, but main belt asteroids whose orbits brought them relatively close to 3I/Atlas's path during its inbound or outbound journey. 2 of them showed small but measurable orbital changes after their closest approach to the comet, changes that were larger than expected from gravitational interaction with a comet-sized body, though not as dramatic as the Trojan departures. The 3rd asteroid showed no detectable change, but it had passed farther from 3I Atlas than the other 2, which was consistent with a mass effect that fell off with distance. With 10 data points now, 7 Trojans plus 3 main belt asteroids, Dr. Margot could start constraining models. He ran simulations with different mass distributions, trying to find configurations that would produce the observed perturbations. A simple point mass didn't work, the effects were too large for a comet-sized object. A distributed mass, like a very large diffuse coma or an extended debris field, could potentially work. But then, why didn't optical observations see that distribution? The coma of 3I Atlas was visible and well characterized. It wasn't massive enough or extended enough to account for the gravitational effects. The best fit, the model that matched the observed perturbations most closely, was a binary system. 3I Atlas as the visible component, a few kilometers across with normal cometary mass, plus a hidden companion about half as massive again, orbiting at a separation of roughly 100 kilometers. The companion would need to be dark, non-reflective, not producing any coma of its own, to have escaped optical detection, but gravitationally, it would contribute to the total mass of the system and could explain the enhanced perturbations on nearby asteroids. That model had precedent. Binary asteroids exist. Binary comets have been observed. It's not unreasonable to propose that 3I Atlas might be a binary system. The problem was the companion's properties. To be as massive as the model required, but not visible in any observations, it would need to be incredibly dark and inert. Darker than any known asteroid or cometary nucleus, essentially black, absorbing all incident light without reflecting or re-emitting anything detectable. That's possible in principle. Some asteroids and comet nuclei have very low albedos, but to be completely invisible at the separations involved, given the sensitivity of modern instruments, required taking material properties to extremes. Dr. Margot published a technical note in February describing the binary model and its implications. The note was carefully worded, presenting the binary hypothesis as one possible explanation for the observed dynamical anomalies, not as a confirmed detection. He pointed out that alternative explanations might exist and that more observations were needed to confirm or refute the binary nature of 3I/Atlas. But the note also made clear that something was going on with this object that didn't fit standard models. Whether it was a binary system, an unusual mass distribution, or some other factor, 3I/Atlas was exerting gravitational influence beyond its visible characteristics. And then there were the other anomalies, because the Mars Trojan perturbations weren't happening in isolation. They were part of a pattern of strange behavior that 3I/Atlas had been exhibiting throughout its passage through the solar system. Dr. Christo, working with colleagues who had been studying other aspects of the comet, started compiling a comprehensive list of all the unusual observations. The surface brightening, documented by the VLT sphere instrument, a 340% increase in albedo over 6 weeks, from 0.04 to 0.17, happening while the comet was moving away from the sun and should have been getting darker. No known cometary process explained that. The brightening suggested active surface transformation, possibly involving energy input from internal sources. The thermal excess detected by Keck Observatory. The nucleus, radiating at 217 Kelvin when it should have been at 180 Kelvin based on solar heating alone. That 37-degree temperature difference required an internal heat source producing about 50 megawatts of power. Where was that energy coming from? The geometric surface patterns seen in Gemini telescope observations. Bright patches arranged in hexagonal and rectangular grids. Linear features intersecting at regular angles. Natural surfaces don't organize themselves that way. Erosion, impacts, thermal stress, they create irregular features, chaotic patterns. Geometry implies structure, implies underlying organization. The inverted temperature gradient measured by ALMA. Subsurface temperatures higher than surface temperatures, 240 Kelvin at a few meters depth compared to 217 Kelvin at the surface. That's backwards. Heat flows from hot to cold. To maintain an inverted gradient requires active thermal management, energy expenditure to keep the surface cool while the interior stays warm. The rotation anomalies reported by several observatories. The nucleus wasn't tumbling chaotically like most cometary nuclei. It was rotating with a period of 6.8 hours, and that period was remarkably stable over the months of observations. Small objects in space usually have irregular rotation, wobbles in precession caused by asymmetric mass distribution and torques from outgassing. 3. I/Atlas rotated like a carefully balanced wheel, like something designed to maintain stable orientation. The spectroscopic oddities. Emission, lines that didn't quite match any known molecule, absorption features at wavelengths that shouldn't be there, isotope ratios that varied in ways that suggested active chemical processing rather than passive sublimation. When you listed all these anomalies together, when you saw them as parts of a whole rather than isolated puzzles, a picture emerged. Not a comfortable picture, not one that fit easily into the framework of natural cometary bodies, but a coherent one. 3I/Atlas wasn't behaving like a passive chunk of ice and rock shaped by billions of years of wandering through interstellar space. It was behaving like something active, something doing things, possibly something that had systems running inside it that were transforming its surface, generating heat, maintaining thermal control, exerting forces on nearby objects beyond simple gravity. The Exodus, when asteroids leave home for no reason. Part 4 of 5. While researchers debated the nature of 3I/Atlas and what it had done to the Mars Trojans, the more immediate practical concern was tracking the 4 asteroids now on Earth-crossing trajectories. Dr. Farnakia's team at JPL's Center for Near-Earth Object Studies took responsibility for monitoring these objects and calculating their long-term orbital evolution. The results were both reassuring and unsettling in different ways. The most concerning in the near term was 2011 UN-63, one of the asteroids that had departed from L4 on January 17th. Its new trajectory would bring it to within 0.08 astronomical units of Earth's orbit, about 12 million kilometers, in August 2029. That's close enough to require careful monitoring. Small uncertainties in the orbit, perturbations from other planets as it traveled through the solar system over the next 3 years could shift the trajectory enough to turn a safe miss into a closer approach or even a potential impact. JPL ran Monte Carlo simulations. thousands of slightly different orbital scenarios accounting for uncertainties in position and velocity measurements, propagating each one forward to see the range of possible outcomes. The impact probability came out at approximately 1 in 85,000. Not high, well below the threshold that would trigger public warnings or deflection mission planning, but not zero either. And here's what made it unsettling. That impact probability was calculated using standard orbital mechanics, assuming no further anomalous perturbations. But if something could kick 7 asteroids out of stable orbits in ways we don't understand, what confidence could we have that similar perturbations wouldn't happen again? Dr. Paul Chodas, who manages the Near-Earth Object Program at JPL, addressed this concern in a statement to planetary defense coordinators. He acknowledged that the Mars Trojan events represented a gap in our understanding of small body dynamics, but emphasized that Earth-crossing asteroids are monitored continuously. Any significant orbital changes would be detected quickly, providing years or decades of advance warning before a potential impact. The standard procedures, track the objects, refine the orbits, update impact probabilities as new data comes in, those procedures still applied. The Trojan perturbations added uncertainty to very long-term predictions, but didn't fundamentally break the tracking and warning system. The 3 other Earth crossers, 1999 UJ7, 2001 FR 127, and 2007 NS2, had less concerning trajectories. Their closest approaches to Earth would be in 2031, 2033, and 2034 respectively, all at distances greater than 0.2 astronomical units. Current impact probabilities were all less than 1 in several million. They'd be monitored, of course, added to the catalog of potentially hazardous asteroids that ground-based and space-based surveys track routinely, but they didn't represent immediate threats. What they did represent was a new class of potentially hazardous object. Asteroids that had been in stable, predictable orbits and then suddenly weren't. That challenged one of the foundational assumptions of planetary defense, that you can predict where objects will be years or decades in advance based on their current trajectories. If asteroids could be perturbed unpredictably by passing comets or other objects we don't fully understand, then long-term predictions became less reliable. You couldn't just track everything once and assume the orbits would evolve according to known physics. You had to keep watching, continuously, ready to update risk assessments if something unexpected happened. The paper on the Mars Trojan departures was published in Icarus in mid-February 2026. The response from the planetary science community was intense and divided. Some researchers praised the careful documentation of an extraordinary event and agreed that it raised fundamental questions about small body dynamics and the nature of interstellar objects. Others were more critical, arguing that the authors had been too quick to rule out conventional explanations and that invoking hidden mass or exotic physics was premature. Dr. Alan Harris from the Space Science Institute, a veteran asteroid researcher, published a response article suggesting that the Mars Trojan departures could be explained by a close encounter with an undiscovered asteroid or small body that happened to be passing through the region at the same time as 3I/Atlas. The timing correlation with the comet would then be coincidental. It was a plausible alternative hypothesis, except that such an object would have to be fairly large to produce the observed perturbations, and searches of archival observations from the relevant time period hadn't found any unknown bodies in the Mars Trojan region. Dr. Christou and his co-authors published a response to the response showing that an undiscovered perturber, massive enough to explain the observations, would have been easily detectable by multiple survey telescopes operating at the time. The debate played out in journal pages and conference presentations through April and May. It was the kind of scientific controversy that advances understanding, different researchers proposing hypotheses, testing them against data, refining models. But underlying the technical arguments was a deeper unease, because this wasn't just about 7 asteroids leaving Mars Lagrange points. It was about 3I Atlas itself and what kind of object it actually was. The compilation of anomalies that Dr. Christou had assembled, the brightening surface, the thermal excess, the geometric patterns, the strange spectroscopy, the mass discrepancy, all of it pointed toward something that didn't fit comfortably in the category of natural cometary body. And when you added the historical context, the evidence from ice cores and ancient texts suggesting that objects with 3I/Atlas's chemical signature had been visiting Earth's vicinity for thousands of years, sometimes catastrophically, the picture became even stranger. Dr. Christou had been in contact with researchers working on those other lines of evidence, the team that had found 3I Atlas markers in the Greenland ice at the Younger Dryas boundary, the scholars who'd analyzed the Dead Sea Scrolls fragment describing a wandering star, the astronomers tracking the 47 Euclid objects with identical spectral signatures. None of these research groups had been coordinating initially. They were studying different questions using different methods, but the convergence of their findings was impossible to ignore. In late April, an informal working group formed, bringing together researchers from these various projects to share data and discuss implications. The group didn't have official status or funding, it was just scientists talking to each other, trying to make sense of observations that individually were puzzling and collectively were paradigm challenging. They held video conferences every few weeks, presented findings, debated interpretations, tried to construct coherent narratives that could explain all the data without requiring assumptions too far outside conventional science. The narratives that emerged were speculative, the kind of thing you'd discuss in late-night conversations at conferences, but wouldn't necessarily put in formal publications. But they were also logical extensions of what the data showed. What if 3I Atlas and the related Euclid objects weren't random interstellar comets? What if they were part of a system, fragments of something larger, or components of a distributed structure that had been passing through our region of the galaxy for thousands of years? What if the perturbations to the Mars Trojans weren't accidental but deliberate, part of some process we don't understand yet? That last question was the most uncomfortable. Deliberate implies intention, implies intelligence, or at least programmed behavior. Natural objects don't do things deliberately. They follow physics, responding passively to forces acting on them. But the Mars Trojan perturbations had looked coordinated. 7 objects kicked out of stable orbits in sequence, 4 of them sent specifically toward Earth-crossing trajectories. The timing, the synchronization, the directional bias, it all suggested something more than random gravitational chaos. Nobody in the working group was ready to claim that 3I Atlas was artificial or controlled or anything of that nature. The standards of evidence for such claims were appropriately high, and the data, while strange, didn't definitively prove anything beyond natural processes behaving in ways we don't fully understand. But they also couldn't ignore the possibility, couldn't pretend that the accumulating anomalies were just a series of unlikely coincidences. By February 2026, 3I Atlas was beyond 3 astronomical units from the Sun, dim and fading as it headed toward the outer solar system and eventually back into interstellar space. Observations continued, multiple telescopes tracking its position and brightness, monitoring for any further changes or anomalous behavior. The brightening surface had plateaued at an albedo around 0.21, nearly 6 times brighter than when first observed in October. The thermal excess persisted, the nucleus still radiating more heat than solar input alone could account for. The rotation remained stable at 6.8 hours, and the departed Mars Trojans continued on their new trajectories, drifting away from the Lagrange points that had held them for millions of years, heading toward uncertain futures. 2011, UN-63 would have its close approach to Earth in 3 years. The others would arrive later. All of them would be watched carefully. Their orbits refined continuously, impact probabilities updated as uncertainties decreased. They were no longer stable, predictable objects. They were travelers now, displaced from home, moving through the solar system on paths that had been chosen for them for reasons we didn't understand, by something that had passed through in January and changed everything in ways we're still trying to comprehend. Science is supposed to provide answers, to take observations and build models that explain and predict. But sometimes science is about recognizing when your models are incomplete, when observations show you things that don't fit existing frameworks. The Mars Trojan departures were one of those moments. 7 asteroids leaving stable orbits simultaneously, perturbed by a comet that shouldn't have had enough mass to affect them, sent on trajectories that preferentially pointed toward Earth. We can document it, we can measure it, we can track the consequences, but we can't yet explain it fully. We don't know what 3I Atlas is, or why it did what it did, or whether it will happen again. So we watch, we continue observing, gathering data, refining measurements. We track the departed asteroids and all the other objects that might be affected by similar encounters in the future. We build better models, propose new hypotheses, test them against evidence. We do what scientists do when confronted with genuine mysteries. We admit what we don't know while working systematically to expand what we do know, and we stay alert, because whatever 3I Atlas is, whether it's an unusual natural object or something stranger, it demonstrated that our solar system is less stable, less predictable, and more vulnerable to outside influence than we'd comfortably believed. That's a lesson worth learning, however unsettling the education might be.